Previously, we've investigated 3 numerical methods, the midpoint rule, the trapezoid rule, and Simpson's rule, for evaluating definite integrals numerically. Here we're going to take a quick look at how we can use technology to facilitate that as the number of subintervals we choose increases. In particular, we're going to explore how a tool called WolframAlpha can do numerical integration for us for those 3 rules and any number of subintervals we want. We'll do a start to finish walkthrough of 2 different definite integrals using this tool. So our first order of business is to go to the website. So we're going to go to WolframAlpha. We'll go to WolframAlpha.com. And you don't need to sign in or have an account to use this. It should be completely free for the kind of work that we're going to do. All right, so we're going to use some fairly specific language when we enter what we want it to do. There's a couple different ways you can do this, but the way that I find it works best is I'm going to type in the word integrate, and then I'm going to enter the function that I want. So the first one we're going to do is the function e to the negative x squared. And you can use the math tools to enter this function so that it looks like it's properly formatted, but I know that if I use the caret for the exponent that WolframAlpha will read that okay. So I've got just e caret and then parentheses my exponent negative x raised to the second power. And then I'm going to tell it which rule to use. So I'll say we'll use the trapezoid rule first. So we just type in trapezoid rule. You don't have to capitalize it. I don't know why I did that. And then we're going to tell it how many intervals we want. So we'll start with, let's say, I don't know, let's do 12. I'm having a hard time typing. 12 intervals. And then we're going to, really having a hard time typing. And then we're going to just let it know our bounds. So we're integrating this from 0 to 2. And I even spelled the word 2 wrong. Okay, so from there, if we use that integrate function using rule with n intervals from x equals a to b notation, it should be able to interpret what we're trying to tell it to do. And you can see it took it word for word, and then it gives us the result, 0.881913. It also gives you the symbolic expansion of the trapezoidal rule below that. It gives you a plot of the graph and the actual integral or the actual integrand versus the trapezoidal rule. And you can see they're pretty close here with 12 subintervals. Gives you an exact result. This thing does not have an analytic antiderivative that our methods can evolve for us. So the answer there's a little more sophisticated than what you need to know. And then it gives you a graph that shows the number of errors versus the number of intervals versus the error. And then you'll see down here, it also gives you a chart of all the different rules and what the result would be using the same number of subintervals. So if you wanted to also do midpoint and Simpson's rule, it's already done the work for you. You don't have to go back and retype it. We're going to do one more example, and this time we're going to integrate the function sine of cosine of x we'll use Simpson's rule this time. Simpson's rule with, I don't know, let's do a lot of subintervals this time just to show how powerful this is. So let's do 200 subintervals. And let's also do this one from 0 to 2. Actually, yeah, 0 to 2, that's fine. And it takes a second to do it, but we see that the result is 0.803863. And again, it gives us the expansion using Simpson's rule. So you see the ones that are multiplied by 2 and the ones that are getting multiplied by 4, plus the first and the last. And again, we have our midpoint trapezoid and Simpson's comparisons, along with a couple of others that we haven't really discussed, but they're all pretty close to each other.